Today we're going to solve this integral without applying the integral's power rule or any other integration rule we know so far. In fact, we're going to use limits. And you may say, how can we use limits to solve an integral? Well, this comes from the definition of definite integrals as the area under a curve. So if we have these integrals from 0 to b of our function x squared dx, this is the area under our function x squared from the point x equals 0 to a point x equals b. And let's say this is the point b. I chose a positive point b, but it can be any real number, also negative b, it's okay. And what this definite integrals is telling us is what is the area under this function. So we can take another approach, that is the limit definition of definite integrals. So what we do is that we divide this area into a lot of rectangles, and the total area is the sum of all the areas of these rectangles. But this is like an approximation, it is not the exact area under this curve. Well, when we take the limit, as the number n of rectangles goes to infinity, so the width of each rectangle goes to 0, of the sum of the area of each rectangle, this is exactly the value of the integrals from 0 to b of x squared dx. This is the exact value, is normal an approximation. But what is the area of each rectangle? Well, we know that the area of a rectangle is its base times its height, and don't use b because we call b the upper limit of our integral, so let's call it L. And now we have to find out what L and H are equal to. Well, if the segment here is b, so as length b, if we divide it, so we have b and we divide it into n parts, we get exactly the width of each rectangle, that is the base of each rectangle, while h is the value of the function at some particular point x. And since those rectangles have equal width, we can say that h is, for example, let's find what h is for the point L is just L squared, because it's the value of the function y equals f of x. So h is going to be L times some integer k all squared. So k could be 1, 2, 3, 4, 5, 6, etc. It's just an integer, and it's telling us what is the height of the kth rectangle. So we can plug these formulas into our areas formula, and we get L times LK all squared, that is L cubed times k squared. Now recall that b over n equals L, so we know that this equals to b cubed over n cubed times k squared. And now we know the area of each rectangle, so we can plug this into our previous sum. Okay guys, this is our sum, and notice that I replaced the index I with k because k is just an integer, it's not a real number, so we can just replace it in the sum. Another thing you have to notice is that b cubed over n cubed does not depend on k, so we can bring it out of the summation. So this is b cubed over n cubed times the sum from k equals 0 to n of k squared. And I haven't taken the limit as n goes to infinity of this summation. This is the approximation, then we're going to take the limit as n goes to infinity of this later on. But now, notice this summation right here. This is the sum of the first k natural numbers squared, and it has a specific formula, that is, so the sum from k equals 0 to n of k squared equals to 1 over 6 times n times n minus 1 times 2n minus 1. We're not going to prove this formula in this video, and we're not going to derive it, but trust me, this equals this sum. So we can replace it into our previous equation, and we get that this equal to b cubed over n cubed times 1 over 6 times n minus 1 times 2n minus 1. And this is our approximation. But now, if we take the limit as n goes to infinity of all of this stuff, we get exactly the value of our definite integral. So this is what we are going to do now. Okay guys, now to solve our integral, we just have to find this limit. And notice that if we plug infinity in this limit, we get the indeterminate form 0 times infinity. So we have to do more work to get to the answer. So what can we do? Well, can you see this n cubed term here? We can distribute it in each term, and we're gonna get a limit we can solve. So let's do it. It's equals to the limit, so n goes to plus infinity of b cubed over 6 times n over n times n over n minus 1 divided by n times 2 times n divided by n minus 1 over n, and we can even bring b cubed over 6 outside our limit because it's just a constant. So this is b cubed over 6 times the limit as n goes to infinity of n over n is just 1. Then we have n over n is also 1, so 1 minus 1 over n times n over n is 1, so 2 minus 1 over n. And now, if we plug infinity here, we notice that 1 over n goes to 0, and also this 1 over n goes to 0. So the value of this limit is 2, so this is b cubed over 6 times 2, because 2 times 1 is just 2, and we can simplify this to b cubed over 3. And this, guys, is our final answer. This is exactly the value of our integral I, and we did it using limits instead of integrals things. So this is very interesting. Don't forget to subscribe to my channel, share this video with your friends, leave a comment below, and as always, until next time, bye.